Now, it turns out that Green's theorem's circulation form is actually just one special case of a much broader theorem called Stokes' theorem. And so let's see how we could think of Green's theorem as just the two-dimensional version of what we're now going to define as Stokes. So this is supposed to just be a visual representation of having tiny little paddle wheels placed anywhere in here, and this is looking at their microscopic circulation, how much they would rotate around the paddle wheel at a given point, adding that up over the interior, and that should give us how much the vector field is actually circulating around the boundary. That's what we proved with Green's theorem circulation form. And as a reminder, that only worked for vector fields in 2D, right? We always were just assuming our vector field F just had I and J components. And so I want you to notice what the extension would be if we went to three-dimensional vector fields. So this is still just looking at a two-dimensional surface in the XY plane. This is the boundary we're trying to find the circulation around. We are not including the vector field in this demo. We're just looking at the region where we'd be placing the paddle wheels. And so notice when we think of this in 2D, our normal vector is just k hat, which is why we end up taking the dot product of the curl vector with k hat to help us get this microscopic circulation at each point. But what if we allowed our surface to not just sit in the XY plane? What if, for example, we wanted to figure out what the circulation was around the boundary of this type of surface? So this is what we're calling this. Well, this is a surface that has a boundary. The boundary you can see is still just that red curve. And the boundary doesn't have to sit in the XY plane anymore either. The boundary could do something cool like this and be actually a curve in 3D. And we could ask, what is the circulation of some vector field like water or gas around this boundary? And it turns out that adding the microscopic circulation everywhere on this surface itself will give us the overall circulation around the boundary. And that's because you're going to get cancellation again on any of the shared interior boundaries here. You're going to get cancellation so that you're going to get circulation around this and then circulation around this. All the insides are going to cancel and you'll be left with just the circulation around the boundary. To figure out the microscopic circulation on the surface, we need to fix the paddle wheel to be normal to the surface to see how much things would spin just on the surface. And so that means that we are going to be taking the curl vector and dotting it with n, our normal vector, instead of dotting it with k. K was just the special case when this was a two-dimensional surface. In that case, your normal vector just became k. But now we can extend this to surfaces that are sitting in 2D surfaces sitting in 3D space. And we can also extend it to curves that are in 3D instead of just 2D. So let's write out what this theorem says. This is just a visual. Okay, so S is now the surface, and C is the boundary of S. So you can think of the surface as being like a blanket, and this is the edge of the blankets, or like a contact lens in the picture over here. It looks more like a contact lens, and then the boundary is C right here. So both of these are the boundaries. And as long as you have continuous partial derivatives everywhere inside the surface S, or everywhere inside your interior surface here, throughout S, then we can find the circulation around the boundary by actually doing a surface integral over the surface of the curl dotted with the normal vector. Yes. And here, the direction of circulation, again, is going to be given by the right hand rule. So you point the thumb in the normal direction, and your fingers would then curl in the direction of circulation. So let's revisit this problem that we just did in example 5. Let's compute the circulation around of the same vector field, F, around the boundary of this hemisphere. And so I want you to notice the previous problem that we just did. Not this one. Here we go, this one. We were finding the work around the circle of radius 2 centered at the origin. And we had this vector field. Now I'm asking us to find the circulation around this boundary of this shell. Now let's see what this boundary is going to be. If we actually draw out what this hemispherical shell is, notice this is z squared is equal to 4 minus x squared minus y squared. So this is the top of a sphere of radius 2, which means that the boundary is going to be that exact same circle that we were dealing with in the previous example. And so what we're doing now, we're going to redo that example now using Stokes' theorem, saying that we should be able to find the circulation around this exact same curve. I have the same vector field that's flowing here, by instead adding up all over this surface, all over this top hemisphere, the curl dotted with my normal vector, ds. And I'm going to show you a picture before we go do it about why they should be the same. Here's my normal vector here. And let's go back to a visual to see why we're going to get the same answer. And then we will try it by calculating this surface integral. So I'll have you put it on pause after I show you this visual and see if you can remember how to calculate the surface integral. Okay, so this is just a quick way we can visualize the region in example 5 that we've been working with. In example 5, we were looking at the circulation around a circle, similar to this type of shape. And I told you option 1 was to do it the long way, which is just actually do the line integral around the boundary. And so we did that by parametrizing. Option 2 was to use Green's theorem, which we ended up finding the K component of the curl everywhere on the inside, which is like a circulation density. And then we added that up on the inside to get us the overall circulation around the boundary. Option 3 is going to be to create any other surface that has this exact same boundary. For example, this hemisphere, and add up the circulation density everywhere on this surface, and we will still get the same circulation around the boundary, because again, you're going to get cancellation everywhere on the inside that have shared boundaries here, which is going to lead us to the overall same answer around the boundary. And so we're going to try this now. This is the third option for this same problem, is actually to do a surface integral over the surface of the curl vector dotted with a normal vector. And if you think about that, what we're actually doing is finding the flux of the curl, because we're taking the curl vector and dotting it with the normal vector over a surface. And we know how to do flux integrals. So we're just doing a flux integral of a curl vector field. I know that's really hard to think about and wrap your mind around, but it's something that we've actually already calculated before. So take a moment, see if you can calculate that surface integral, and we'll come back and check in. Okay, so here we go. We are now going to use Stokes' theorem to, again, the goal is to figure out this line integral. But we're going to say, instead of doing this line integral, let's do this double integral over this surface, because they need to be the same based on Stokes. And so we just find this vector field, And then you just imagine really that you're finding the flux of this new given vector field. Because really, that's what we used to do when we were finding flux integrals. You can think of this as like your whole new G dot n ds, and that's really a flux. Okay, so we need to rewrite our n ds, which is right here. And then we're just going to simplify. And you're going to see we're going to get back down to the exact same double integral where we left off in example 5. You switch to polar, do the same thing, and we get the exact same answer. So this is the hardest way to do this problem. I wouldn't, if we really just wanted to know this circulation around the boundary, I probably would have just smashed down this hemisphere and just integrated instead over this region because they both share the same boundary. And it's a much easier integral just to do that double integral instead of the surface. But we were showing through this process that Stokes' theorem holds and that you can get the same answer either way.